Today, we have a very special treat for you. Many of you already know him, but if you don't, allow me to introduce him anyway. Professor Callum Littlejohns, coordinator of Cornerstone. Hi, Callum. I'm really looking forward to your talk today about silicon photonics and how it's all made. I'll stop sharing the screen and I can over to you.
Well, thank you very much, Ramsey, for the introduction. And hi, everybody. It's a pleasure to be here. Thanks a lot for committing an hour of your time to spend with us this afternoon or morning or evening, wherever you happen to be. The topic of this talk is how it's made, which of course is a very broad subject that I could spend hours talking about, but luckily for you, I'm not going to. We're going to try and squeeze it into 45 minutes. So that means I can only really touch the sides on what's possible and really start with the basics of how silicon photonics is built. This is an overview of my talk. I'm going to rip up the rule book and start with conclusions. The reason for doing that is that I've made an assumption, which may or may not be accurate, that many of you are designers. So I'm going to start by giving you some conclusions so that you can bear them in mind throughout the rest of the presentation. Then I'll introduce you to what a cleanroom is and what it's like to work in one. I'll talk you through a typical fabrication process flow. In this case, it will be a carrier depletion based silicon photonics modulator. I'll touch the sides of a couple of commonly used fabrication processes. If we have time, I've got 3 case studies, but I might have to skip them, or at least some of them. Then I'll briefly introduce the foundry ecosystem across the world. Of course, Cornerstone is one of many foundries that is growing by the year. There are more and more popping up. And then I'll conclude with a couple of rules of thumb for designers, just as considerations that are important related to the fabrication process. So let's do last things first then. So we'll start with the conclusions. And I put a point there in bold and underlined. As a designer, you'll never receive dies that exactly match your designs. Don't be scared by that statement and put off. But what I mean by that is that there are always tolerances involved. There are always variations across wafers. There are variations from batch to batch. There are variations within your chip. So as a designer, it's very important that you're aware of that from the outset, and because that means that you can consider these tolerances within your design. You can make more robust designs. It means you can get things that work the first time. And it just means that you'll have better, high quality designs at the from the outset. And all foundries will provide you with a set of design rules, and this will guide you on what's possible within their particular fabrication processes. So definitely pay close attention to them and make sure that you follow the design rules, particularly around minimum feature sizes and things like that. And lastly, fabrication is very challenging, and maybe that will become a bit clearer as we go through. And just to sort of emphasize what I mean on the first point, on the left hand side you'll see it's a thickness map for the top silicon layer thickness on an SOI wafer before we even touch it. This is straight out of the box from the supplier before we even do any fabrication. So what you'll notice is that there's a variation of the full range is about 6 nanometers, but if you exclude the outer ring, you still have a 3 or 4 nanometer variation. This is in the silicon thickness before we even do any fabrication. So what that means is that a die that's from one part of the wafer is going to behave differently to a die from another part of the wafer. And as we go through the fabrication processes, we sort of build up these tolerances. So it's very important to know that will have an effect on your circuit, and it's not going to look 100% exactly the same as what you draw. Okay, so taking a step back, as you probably know, all silicon photonics, not all, the vast majority of silicon photonics fabrication happens in a clean room. So I've asked the question here, how clean is a clean room? And the answer is it depends, as with most things. There are a number of different classifications that are shown in this table here. And it's all about the number of particles per cubic meter of air. So the lower the class in terms of the number, the higher grade it is, the fewer particles you have in the air. And the red box there shows the classification of clean rooms that we have at the University of Southampton. They're either ISO 5 or ISO 6. The higher grade ISO 5 is reserved for the lithography areas, because here we have exposed wafers. But where the majority of the other processing happens, we only have a class 6 because most of it happens in a vacuum chamber. So it's not quite so critical that you have a really clean environment. So there's a big ecosystem around a life support system, if you like, around the clean room that keeps it clean. And its biggest challenge is fighting against the people in it. So by far the biggest contaminant in a clean room are the people. And that's why the very latest sort of state-of-the-art clean rooms that will do the highest technology nodes, electronics, won't have any people in, except possibly to service the equipment. And the table here shows you how many particles are generated by a person doing various different things. So if you see, if I'm getting up and sitting down in the clean room, I'm creating 2.5 million particles that are bigger than 0.5 micron per minute. Now, if I just flick back to the previous chart, to maintain an ISO 5 standard, we can only have 3,520 particles of that dimension in that in a cubic meter. So you can see how it's quite a system that's needed in the background of a clean room to keep it clean and to reduce the contamination risk on your wafers, because of course 0.5 micron is reasonably big when it comes to typical dimensions of a device. So if that particle ends up on your wafer, it can destroy the wafer, or at least that device entirely. Now on the left here's our clean room manager, showing you the typical attire that you'll see in clean room. So you'll notice that the only bit of skin that's really exposed is around the eyes, and normally he'd be wearing goggles as well once he steps into the facility. So everything's covered over to try to prevent particle generation that could contaminate your wafers. There are a number of banned items listed there, plus more. I mean, the crucial thing is that these generate lots of contamination. So we clearly don't want that in a clean room environment. And notice that paper's listed there, which generates a lot of particles. So we have to buy special clean room paper to be able to take into the clean room. So health and safety is a very big consideration. This little clip shows somebody working in a wet room environment. So they're just loading a batch of, or in this case, a single wafer into an acid tank. So you'll notice that we now have even more personal protective equipment. We've got acid-proof gloves, a smock, and a visor. This is just to, make sure that the people in the clean room are very safe. And we at Southampton are very aware of what can go wrong. This is a picture taken in 2004 of what used to be the previous version of the clean room. This building here caught fire. It was a very, very large fire, as you can see. And just for reference, the Cornerstone team sit in this building over here. So it wasn't the fault of the health and safety protocol, just to be clear. Nobody was at fault for this fire. It's just a unfortunate situation. But due to the hazardous gases and the hazardous chemicals and things like that are used in the clean room, it was a very difficult fire to deal with. The fire services, in fact, just had to let the building burn down because they couldn't risk the people entering because of some of the toxic gases and things like that are used. So, but you'll be pleased to know that it's since been rebuilt, reopened in 2008. And we're lucky enough to be able to use the excellent facilities that have come out of that now. And if you're interested, you can follow this link and you can do a virtual tour of the clean room. You can step inside. It works in a similar way to Google Maps. You can go and observe different pieces of equipment, have a look around. So please, I encourage you to do that after this webinar if it's interesting to you. And it would be negligent of me not to mention the brilliant Cornerstone team. Coming back to the subject of the talk, how it's made, the reality is this is how it's made by this team of very passionate, dedicated and talented technicians, researchers and other professionals. And a particular highlight, I think, of this team's achievement is that earlier in this year, they managed to deliver a full MPW run within 3 weeks. So the users of that particular course submitted their designs on day 0, and by day 21, their chips were in the post, ready for them to receive. So if you're wondering how it's made, it's by these people. Okay, so that's a very brief introduction to a clean room. I'm now going to move on to talk about a typical fabrication process flow. Now, this is on the left a GDS diagram of a carrier depletion silicon photonics modulator. And in this particular case, it consists of 9 different layers. So this is 9 different lithography steps we have to go through to build up this circuit. And if you consider the cleaning steps, the etching, the various other processes, it comes to roughly 70 or 80 individual fabrication process steps to be able to build this. And in a second, I'm going to show you a short animation of how that happens. But just lists there that the different layers that are used to build up this device. Okay, videos are working so far, so good. So we start with an SOI wafer. We then spin it with a photoresist, and I'll come on to give you more details about lithography processes in a moment. The first thing that we would do is pattern it with the grating coupler layer. Now, the reason that we choose to start there is that this is the shallowest etch. And as we build up topology on the wafer, the process becomes more and more difficult. So we start with the shallowest etch to simplify the subsequent steps. So once we've done that, we strip the resist. We then move on to pattern the next layer. So this is now layer 2. In this case, it's a P-type doping layer. And what we're doing now is we're implanting selected regions that are later going to become waveguides. We then strip off that layer of resist and we move on to layer 3. But before we do that, we deposit a full layer of silicon dioxide that we call a hard mask. It's called a hard mask because of the material is hard relative to a photoresist, which is much softer. So now what we've done here is we pattern the waveguide layer by lithography. We then etch away the hard mask. We strip the resist. And then using that hard mask, we do a partial silicon etch into the top silicon layer that form rib waveguide structures. So at this point in time, everything that we've drawn is now a rib waveguide. But what we then subsequently do is we pattern another layer that we call the rib protect layer. What this does is any region of the device that we want to keep as a rib waveguide, it protects with photoresist, and regions that we wish to become a strip waveguide. any regions that we wish to become a strip waveguide are exposed to what I'm going to do. Bear with me. Right, sorry, technical glitch. I thought I could pause, but I couldn't. So I just need to bring the video back to where we were. I knew we wouldn't have a seamless call. Okay, where were we? Yeah, this is where we were. So I'm not sure if when I go full screen, it's going to allow me to carry on playing here. So just while the video plays, I'll stay in this sketch that we just performed there. I can pause it here. It will etch away regions that aren't protected by the resist or the previously patterned hard mask. And the beauty of this approach is that we have a self-aligned process so that we don't have any alignment error between the rib waveguide here in this region and the strip waveguide here. So we've now got 3 different silicon etch depths. We've got the gratings, the rib waveguide and the strip waveguides. We're now going to go through 3 more implantation levels. So the first one is to do an N-type doping level, and this is formed on the other side of the waveguide. So as we zoom in now, what you'll notice is that at the outset, the entire waveguide region is P-type. That's done deliberately to avoid alignment errors. But once we do this P-type, this N-type, implantation step here, we now implant 1/2 of the waveguide with our N-type, and that forms our PN junction. We do an angled implant so that we can implant into the sidewall of the waveguide, and the beauty of this approach is that it means that this junction position is defined by the implant energy rather than any alignment error on this lithography step, noting that actually this lithography is positioned in the center of the waveguide, but this hard mask is blocking the implant from the top. So that means that we get very reliable and repeatable devices. I'm going to skip over the next 2 implant steps because what we do is we have a high doped region on one side of the waveguide and a high doped region of N-type on the other. Just in the interest of time, we'll skip over that. So we've now got 4 implantation levels in our waveguide. So the next thing we do is to deposit a top cladding. So this forms a protective surface, but also isolates the optical mode better into the waveguide. We need this cladding so that we can add metal on top in a later step. But of course, we need to be able to access the doped region. So the first thing we do is to etch what's called via. So this opens channels in the cladding layer into contact with the silicon. As you can see, we strip away that resist layer. We then deposit a metal layer all across the wafer. We spin this with photoresist and pattern it to define the electrodes. And the final step that we're going to do is to etch away the metal in the regions that we don't want it, and that forms electrodes. So that's a whistle-stop tour of how we would build a silicon photonics modulator in a sort of schematic animation. So I'm going to go back to full screen now, because it should. Okay, so what I'm going to do now is talk you through a couple of the details of the fabrications, individual fabrication steps. And those of you that come from an electronics background will note it or be familiar with many of these. And that's, of course, is one of the beauties of silicon photonics, that we're really utilizing decades of knowledge from the electronics industry and using on the whole the same processes. Sometimes they have slightly different requirements, but generally speaking, we're using the same equipment. There are 3 there that are bold and underlined. Those are the 3 that I've selected to go into very basics of, and the others, unfortunately, we don't have time for. So starting with lithography, because it's really the fundamental process within any semiconductor process flow. This, in a nutshell, is the process of defining your design onto the surface of the substrate. And the way it works is we spin what's called a photoresist layer onto the substrate. This is done at high RPM, so we get a nice uniform coating. And this contains a photosensitive compound that's suspended in a solvent. So once we've done this spinning step, we then bake the wafer, and that evaporates the solvent, leaving behind our photosensitive compound. And this will usually happen in a yellow room environment, and it's yellow because it filters out the wavelengths of light that actually interact with the photosensitive material. If any of you are keen photographers, this is, you know, almost exactly the same concept of how you develop an old school photograph. So once we've got our photosensitive layer on our wafer, we then put it into a lithography tool and we expose it to light of a particular wavelength, but it's a selective exposure. So we have a mask layer that blocks particular regions of the wafer and exposes others. And this causes a chemical reaction in your photosensitive layer that when we then subsequently put it into a developer, the exposed regions, if it's a positive tone resist, are then removed by the developer, leaving the substrate exposed. Once we've done this, we can then go on to another step that could be an etch, it could be an ion implantation, or it could be a number of other things. And there are a number of different types of lithography. The three most common are listed here. There are more. The most basic is what's called contact lithography, and as the name suggests, in this case, we simply contact the mask layer on top of the substrate. And this is a very accessible tool that almost every clean room around the world will have access to. So it's very affordable, but it does have a limit in the resolution, because you'll get some diffraction of the light from the bottom surface of the mask. But a far more complex tool is a projection lithography system, and now in this case we move the mask away from the surface of the wafer, and we have a big lens in the middle. And in the little diagram there, it's shown as a single lens, but in reality it will be a very complex sequence of lenses, and that lens focuses the light that's coming through the mask onto the surface of the wafer, and usually it will shrink the image. In the case of the tool that we have, it's by 4 times. So what this means is that it reduces the requirements on the dimensions in your mask, because the dimensions you achieve on the substrate are 4 times smaller than on the mask. This is really a mass production tool. The latest tools are capable of doing several hundred wafers per hour, and it can have a very good resolution, down to sort of 25 nanometers for the very expensive state-of-the-art tools that tend to not be used for silicon photonics, because that's really overkill. But there are more affordable sort of legacy tools that have a higher resolution limit, but I'll come on to that on the next slide. Another very common lithography tool is an electron beam system. This is different from the other two in that it's a direct write tool. So we fire a beam of electrons at a resist layer that in this case is sensitive to electrons. But it does mean that it's a very slow process. We have to effectively draw everything that we want on the wafer. So if I compare that to projection lithography, it literally could take, say, 2 days to go through writing a waveguide layer on an 8-inch wafer using E-beam. But the best thing about it is that we can achieve a very high resolution, because clearly the wavelength of an electron is much smaller than that of light. So this gives you the very best in terms of resolution and capabilities. So a little bit of detail about projection lithography, there are a few different systems that are commonly used in silicon photonics, and I've listed the 3 most common here. And the 248 and 193 refers to the wavelength of light that we use. I've listed the sort of typical resolution and overlay alignment parameters on the slide, so I won't go through them. I would say that the more legacy tools are useful for prototyping, because you can access them in both 8-inch and 12-inch. The later tools that are higher specification generally are only available in 12-inch, so that, you know, it becomes far more expensive to access these, but clearly you can achieve better performance from them. So this is just a video of our lithography system. Here we're loading a cassette of wafers. It's all automated and handled by robotic arms. So what we're doing here is loading a wafer. We're now spinning it. Here you'll notice it's spinning at very high RPM. We're coating it with a photoresist layer. We're now going to move it to a hot plate to bake it. And then it gets passed into the scanner. What we didn't show is that actually there's a preliminary step of spinning it with an anti-reflective coating. So there are actually 2 layers that we spin on. This is the process of patterning the die on the wafer. Here it's sped up. And once we've done that, the wafer gets passed back into our track system, and the development process happens. So this is the development being automated in this way. Everything can be very controlled, and here we have our nice output wafer.